So my name is Al Neely. These are my co-authors here. As part of a research group at University of Tübingen for my postdoc. Uh, this talk here is going to quantify rates of drainage divide migration, particularly the rates involved with driving river captures in a landscape developed in gently dipping layered rock. And our study here was funded by the Bundesgesellschaft für Endlagerung. That is a government company in Germany responsible for storing nuclear waste. So that's where this talk begins. One approach to storing nuclear waste is to sequester it in these deep geologic repositories. We're going to bury this at a depth greater than 300 meters. You need to keep it there for 1 million years. And an important aspect of this is limiting the erosion of the overburden, which could bring the repository closer to the surface, which we don't want. So the BGE hired a bunch of geomorphologists to quantify rates of erosion across southern Germany, which is a really great opportunity to do science. So primarily we were collecting catchment averaged erosion rates derived from cosmogenic radionuclides. There are 192 of these watersheds now over this region. In some localities, we can calculate river incision rates. Here's an example from Bishop, 1995, for the river capture. So the Green River here used to be flowing where the Blue River is. If the capture redirects that drainage and causes the incision of the gorge, if there are sediments that are left behind from that former drainage network, we can calculate the incision rate as the difference in erosion, so the incision of the gorge, in the age of the sediment. So if we put those two sources together in these simple box plots, this is erosion rate on the y-axis. I put up a few horizontal bars here. If you're storing nuclear waste, ideally you want these erosion rates to be as low as possible. If they're above the orange bar, that's 300 meters per million years. That becomes a pretty substantial hazard. And outliers are certainly important in this regards. And one of those outliers is the Wutach drainage capture. So this gorge here, incised a few hundred meters of topography in less than 20,000 years. So it's a short pulse of rapid erosion, and that's a major concern. You need to know kind of how these happen and where they might happen in the future. So that motivates this talk, which is to constrain the rates and patterns of divide migration that lead to river capture. So the nice review paper here by he et al. Nature goes over 3 different mechanisms, common mechanisms to move drainage divides. So gradual divide migration. In all these cases, you have contrast of base level between 2 drainage networks. But in gradual divide migration, basically each tributary keeps capturing the same amount of drainage area. And no gorge is forming, and the drainage network is erased from the drainage system that is losing drainage area. In a bottom-up river capture, you have one area along the divide, makes this little notch. So there's faster divide migration rate there than adjacent locations. And that allows redirecting a large amount of drainage area into a different river system in Carbon Gorge. This talk is going to quantify the relative rates of divide migration involved in that process. I put in overspill here because the result of an overspill looks very similar to a bottom-up river capture. So you need to be pretty careful about distinguishing these two. Happy to talk about that more. Don't have time in this talk. Anyways, taking to southern Germany now, the drainage networks here are very complex. This figure is also very complex. We cannot choose what the topography looks like. This is what the topography looks like here. But it's interesting for a number of reasons that I'll get into. Where are we first? We are at the drainage divide, European water drainage divide between the Rhine and the Danube. So tributaries of the Rhine here, the Main and the Neckar, and then the Danube up here in blue. And what's great about this setting is there's a clear driver of drainage divide migration and a record of rock uplift that drove that drainage divide migration. So the tributaries of the Rhine, the Main and the Neckar, the base level of those tributaries has been lowered by the Rhine-Graben, which is an Eocene-aged normal fault structure. So base level's low over here, higher here in the Danube, divides are moving. Even better, in the strata in the Rhine-Graben, there's a record of rock uplift patterns. So in the base of the Rhine-Graben, below the syntectonic sediment, Mesozoic strata are tilted to the south, indicating pre-Eocene uplift to the north. Right? Then drainage off to the southeast. That condition switched in the Miocene. So you have an unconformity then in the syntectonic sediments in the south. And the south was uplifted. And portions of the drainage network reversed their flow direction. So these main stem rivers here in pink. Okay. And then there's barb tributaries that retain that southeasterly flow direction. Even better, we can constrain the rates of rock uplift over this time period because there's an uplifted marine paleo shoreline, now at an elevation of 900 to 450 meters. The rock uplift rate is known. And the geology in this region, I would say, is complex geomorphically, but simple structure. Okay, so it's a gently folded layered stratigraphy, which allows us to kind of trace patterns of rock uplift across the landscape. There's no real significant large faults other than the upper Rhine-Graben. Those strata form these cuestas, and we're kind of preparing the erosion of the front of the cuesta from these barb tributaries that are draining the backside of the cuesta and rerouted along the reversed rivers to the front of the cuesta. Okay, so we have two ways of estimating divide migration rates. Again, in the reverse main stem rivers, and then the interfluves of those barb tributaries that come up to the cuesta. So in the main stems, this is a profile of one of these reverse main stem rivers with stratigraphy kind of cartoonized in the background. We can identify these river reversals because there are river gravels that one grade in the opposite direction of the current main stem river, and they include sediments that are derived from bedrock units that are only exposed in the current downstream direction. So this is what that looks like. There are usually few, but diagnostic mammal fossils for these deposits, which allow us to constrain age. In this case, these are early steppe elephants from the early Pleistocene. Steppe elephants of the early Pleistocene. So given an age of that deposit, and knowing that the divide had to be further from the present divide than that location, we can calculate a minimum divide migration rate between that deposit and the present divide position. Okay, that's approach one. This is a more conventional approach to estimating divide migration rates that we use on the interfluves. So you'll have a steep side and a gentle side. We have the steep sides, those are going to be squares in this talk, and the gentle sides in circles. And in layered stratigraphy, you have to be pretty careful about doing this. We'll get into details of this in the paper we're preparing. Importantly, we just basically constrain ranges of possible divide migration rates. And the most important aspect of that in this case is the maximum divide migration rate, which we assume in that case that the erosion rate on the backside of the cuesta or tributary is 0. Okay, so these are the catchment average erosion rates with each catchment or catchment pair as a separate column. Catchment pairs have both a square, so that's the steep side, and then a circle, which is the gentle side of the divide. What we see here, this is in now kilometers per million years. These erosion rates are roughly similar to the long-term rock uplift rates. Necker. If we bunch those together and look at populations, samples, we see that there isn't really a huge difference across these divides. That is then reflected in the divide migration rate of interfluves. So even the maximum divide migration rates, again, these are ranges, the log scale, we're being pretty conservative here. Those are more than 10 times less than the divide migration rate in the reverse main stem rivers. And those divide migration rates in the reverse main stem rivers are about 100 times faster than the long-term rock uplift division rates. So those divides in the main stem rivers are moving very fast and driving river captures, which then further accelerates the rate of divide migration within the main stem rivers themselves. So it's kind of a twofold thing. Divides of the inner fluids are not moving, so there's a larger drainage area to capture in those tributaries with stable divides, and that drainage area is routed into main stem, which experience the more significant divide migration. All right. So in conclusion, I promise this little cartoon will make some sense after I read these. Rates of divide migration can exceed rock uplift and incision rates by 100x. Those are long-term rates. Captures are enhanced by both it's this contrast where there's portions that have stable divides, relatively stable divides, and then that routes larger drainage area into the main stem rivers where the divides are moving much faster. And a result of that is that incision is highly variable across the landscape, which is important if you're thinking about storing your waste. So this is a little cartoon and illustrating that where we have the Barb tributary divide. He's basically encouraging the main stem river divide to go. And with that, I'll take questions. Thank you very much.